Hi guys, hi Kuti. So yes, we are going to start our class today. So let's have a quick revision on what we had completed. So in this class, I will be starting with energy, power, and series and parallel combination of resistors today. And also we will solve few problems on that. Yes. Hi Bhargav, good afternoon. So guys, waiting for more people to arrive here in Zoom. Okay, inform your friends and everyone to join the class. Okay, so everyone in YouTube also please inform your friends. Yeah, let us improve our strength of how many people are here in the YouTube live class. Okay, so guys, so yeah, meanwhile, till the class starts, we'll start our class exactly by 3 p.m. So till then, once the technical check, please let me know if my voice is audible clearly and if my backboard is visible. Then if the presentation is visible to you all clearly. Okay. In addition to that, if you have any issues in my voice or any other voice modulation or any other issues, let me know. Okay. Yes, I hope. Yeah. Today in Bangalore, so I'm in my home. So all these days I was in Jammu where I was working in from school. So today I'm back in my home. So I don't know. Yeah, let me know. There might be some monetary issue, but you know, at any instant, if my voice is inaudible or at any instant if my screen is blank or anything like that, let me know. Okay. So Kriti, yeah, you say the voice is not audible, right? Is it audible now? Please reply in the chat box now. My voice gets it. Hi Rakesh, good afternoon. So is my voice audible, Rakesh? Uh, YouTubers, please, yeah, hi guys. So is my voice audible, guys? Is there any issue with the voice? Please let me know. Okay, thank you, Rakesh. Thanks for the confirmation. Okay, so it's 3 o'clock, and yeah, waiting for more students to arrive. So please inform all your friends so that they could attend the class and we could start our discussion. Okay. I hope today there was physics test, is it? Acha. Okay, they still have the test. I mean, you test India, Rakesh. I guess all of them have the physics test today or tomorrow. Okay, now just okay, it's over now. Okay, it may take some time for all the other students to arrive, is it? So yeah, then we'll start our class with the number of students available. I'm ending the poll and let's begin. So in our previous class, we had studied about Ohm's law, right? So we'll just have a brief introduction on what we studied, or brief revise on what we studied. So in previous class, we studied about Ohm's law. So what was Ohm's law? So if we have any conductor, say what there was Ohm's experiment, so you took a conductor and applied a known potential to this conductor, and he checked the potential. Yes, he applied a known potential and he checked the current flowing through this conductor. Then, so he found that so by keeping an ammeter and an voltmeter, he found the current and voltage respectively on the conductor. So across the conductor, he measured the voltage, and through the conductor, he measured the current. So he found that the current there was a peculiar. I mean, there was this unique observation that the current flowing through the conductor was always proportional to the current, sorry, voltage, or the current flowing through the conductor is always proportional to the potential difference applied across the conductor. So this later was given as Ohm's law. On equating, we got I is equals to V by R. So I is equals to V by R, where R is called as the resistance, right? So what is resistance? We discussed that also. So the resistance is the opposition for the free flow of electrons. So whenever we have a conductor, that conductor, if we have, so I had a conductor here. Now I had connected this conductor to a potential V, and there exists electric field. Yes, exactly, Rakesh. So yes, the electrons start to flow from this end to the other end. So in its course of flow, what happens? It collides with other particles. So there were some atoms or other electrons or other charged particles. It collides with one another. So it will not follow a straight path. It will follow a zigzag path and comes out of the conductor, right? So my electron comes out of the conductor this way. So there was some opposition for free flow of electrons. This opposition was called as the resistance. Then we discussed about the resistance. So we wrote the Ohm's law in terms of V is equals to IR and I is equals to V by R, and this relation we also try to find the resistance of the conductor by using R is equals to V by I. This formula was used to find out the resistance. So the SI unit of resistance was ohms, which we found. Then there was the resistance also depended on. This was first thing. Second thing, the resistance. Resistance was directly proportional to what? This resistance depends on geometry of conductor also, right? So my resistance was dependent on geometry of conductor. So what were the factors that depended on? So the resistance of the conductor depends directly on, the resistance was directly proportional to length and inversely proportional to area. More the area, less resistance. More the length, more the resistance, right? So this was equated as R is directly proportional to L is proportional to A. On equating, on removing the proportional symbol, we got a new constant that is called as resistivity. So this R is equals to rho L by A. We got this, and whatever the rho we have is called as the resistivity. Okay, resistivity again is a material property. It's the material property, and it varies from one conductor to other conductor. Next thing which we studied was alternate form of Ohm's law. What was the alternate form of Ohm's law? Can somebody reply, guys? Alternate form of Ohm's law. What was the alternate form? So what was happening? So we know the resistivity is given by rho. So inverse of resistivity. What was inverse of resistivity, guys? So there was one more term called as inverse of resistivity. What is the inverse of resistivity called as? Come on, guys. Answer, please. Answer in the chat box. Reverse. Yes, exactly. It was called as the conductivity, right? So there was something called as conductivity. Okay, good. Yeah. So the inverse of resistivity was called as conductivity. So conductivity was nothing but 1 by rho, or it's given by sigma. Sigma is equal to 1 by rho. So in our previous class, we studied sigma as ne square tau upon m. From here, we got another expression for rho. What was the other expression for rho? If sigma is equal to n square tau by m, my rho will be equals to m by ne square times of tau. So this was the other expression for rho. And using the resistance formula, I get rho is equals to Ra upon L. So these were the other formulas. So we studied using these relations. We tried to derive another expression for Ohm's law that was J is equals to sigma E. So this we had already derived. Okay. Please check that. Okay. Next, we studied about limitations of Ohm's law. What were the limitations of Ohm's law? So there were few limitations for Ohm's law. So Ohm's law was not applicable to all conductors. Where it was not applicable to all types of conductors. It was limited to few conductors only. Yes, cool guys. Yeah. So limitations of Ohm's law. So Ohm's law was not able to apply. It's not applied to which were the things, which were the different types of things which were not, which did not satisfy Ohm's law. First thing was unilateral devices. Guys, what is meant by unilateral devices? I told you. Yes, exactly, Rakesh. Cool, super. So they don't allow same amount of current, okay? So if a current can flow in this direction, the same amount of current cannot flow in this direction, okay? If I is the current flowing through this direction, then if there is another current flowing in the opposite direction, it's not possible. So it doesn't allow the flow of current in other opposite direction. So such networks were called as unilateral networks. So these did not, so the unilateral networks like diodes, transistors, etc., did not obey, doesn't obey Ohm's law. Okay, so this was learned. Next, there were semiconductors. Semiconductors, what happened? So in all other conductors, so we saw that the temperature dependence of conductors. When the temperature increases, what should happen to the resistance, guys? If my temperature increases, what will happen to resistance? If the temperature increases, the resistance also increases. But in case of semiconductors, if temperature increases, resistance decreases. So here, this was not applicable. So this the Ohm's law was not applicable to semiconductors. So in previous class, yes, I'll be continuing with the class. Cool. Okay, guys. So in today's class, in previous class, we also studied about temperature dependence of conductors. So what happens? So whenever we try to heat. So if we consider a conductor, and if we heat this conductor, what happens inside the conductor? Their atoms present in the conductor starts to vibrate. Starts to vibrate. Why? It gains some kinetic energy. It absorbs all the energy present inside, all the energy from heat. And if what happens, it absorbs the heat energy and gains the energy and starts to vibrate. Okay, when they start to vibrate at room temperature, it will be normal, but when we heat it, it starts to vibrate, and all these electrons will start to collide more. So there is more collision possible, and there is no path for electrons to go. So this way, there is more opposition created for flow of electrons. Okay, from here, what happens when the temperature increases, the resistance of the conductor also increases. Okay, so this is what we had learned in our previous class. As temperature increases, the resistance also increases. So we studied that relation is given. So it's given by rho t is equals to rho naught into 1 plus alpha into delta t. So this is given as the rho t is the temperature. Okay, it's the temperature at any given resistivity at any given temperature. Okay, well, and rho naught is the resistivity at standard or reference temperature. Alpha was the temperature coefficient of resistivity. Then the dimension of alpha, so we studied that alpha was 1 by t or 1 by k. So we also checked that the resistivity is positive for all conductors. So the coefficient of resistivity, the coefficient of resistivity alpha is always positive for all conductors, all metals. Okay, so we know that R is equal to L by A at temperature T. On substituting or on measuring the resistance at any given temperature RT, so we try to derive this expression. So we know that as temperature increases, the resistivity increases with this expression. Rho t is equal to rho naught into 1 plus alpha delta t. And similarly, my length. So in our 11th standard, we had studied that on heating. Say if I have a conductor, if I have a metal surface, on heating this metal surface, what happens? Heating it. If I heat it, what happens? In 11th standard, we had studied this, guys. So on heating, what happens? This metal expands, right? Expands. On heating, the metal expands. So this expansion was given by the thermal expansion coefficient alpha L. So this expansion, it was given by thermal expansion coefficient. Okay, so that is nothing but my alpha L. So this is my alpha L. Okay, so we use this. So it varies as L naught into 1 plus alpha L times delta T. And similarly, when I heat the metal or when I heat any object, what happens? Even that object tries to expand area wise. So that was given by A naught into 1 plus 2 alpha L delta T. So this way my length and area also increases, but this is of the order 10 power minus 5. So this is negligible amount. So now what happens? I can, so yeah, I can rewrite this expression as here. So alpha L is very less. So at the RT can be equated as RT is equals to R naught or rho naught into 1 plus alpha delta T into L naught, where L naught is the initial length. So this change in length or change in area is very negligible, but whereas the change in resistivity is more when the temperature increases. So that is given by RT is equals to rho naught L naught by A naught into 1 plus alpha delta T. So I finally get that. So this can be neglected. So finally I get the value of L naught and A naught can be neglected, or what's happening here? Rho naught L naught by A naught, right? What is rho naught L naught A by A naught? Rho naught L naught by A naught is nothing but R naught, initial resistance before temperature rise. Before temperature rise, whatever the resistance I had, that is met by R naught L naught by A naught. Okay, so I'm going to write this. So this is the resistance. So this is how my resistance varies as my temperature increases. So I'm going to use this formula. So here I spoke about resistivity, but at the end of this derivation, we are speaking about resistance. So where RT is the temperature or resistance of any conductor at given temperature T, and R naught is the reference temperature. So resistance at 0 degrees Celsius. Whenever I have 0 degrees Celsius, what will be the resistance that is given by R naught? Whenever I have any increase or decrease in temperature, that is given by RT, and alpha and delta T is the change in temperature. Okay, delta T is the change in temperature. And alpha, we know that it's the coefficient of resistivity. Okay, temperature coefficient of resistivity. So this was the expression, guys. So this we had studied, and we had checked for other conductors also, right? Say at temperatures much lower than 0 degrees Celsius, the graph, however, decreases and deviates considerably from straight line. So this graph at temperatures, so at below 0 degrees Celsius, when we go, if we reduce the temperature further, the conductivity increases, resistivity comes down. Okay, so that we'll study as superconductors. So there will be a separate topic if there is, if it permits, but I think that's not in your syllabus. So there is something called as superconductivity. I hope most of you know that. So there is something called as superconductors, or the conductivity of some metals. What happens to increase the conductivity? They decrease the temperature. Okay, so there will be formation of superconductors. Okay, so that's a separate discussion, but that's not in the syllabus. But what happens as we increase the temperature, the resistivity increases. So that we check, and we also check for some materials like nichrome, the nickel, iron, and cobalt. Sorry, the nickel, iron, and chromium alloy. So for this alloy, it exhibits a very big dependence of resistivity with temperature. Why? So I think Hari Prasad had asked this question. So why does this nichrome shows very less big dependence on resistivity? Because answer is, so what happens in the structure, say the nickel alloy, nichrome alloy, the nichrome alloy at its base level, say at valence electron. So at its valence band, it has very less number of electrons. The nichrome alloy has very less number of electrons, okay, to conduct. So since it has very less number of electrons, since, okay, again this is a conductor, so this is a conductor almost what is it, the conduction band and valence band is almost overlapping. So, but what happens in nichrome alloy, there is very less number of electrons, So even if I increase the temperature, what happens? Since there are very less number of electrons, the conductivity does not vary. So resistivity also does not vary. So for nichrome alloy, it shows very weak dependence of resistivity. I hope this is understood, guys. So nichrome alloy, why does it show very weak dependence of resistivity? Is because it has very less number of free electrons in it. So even on increasing the temperature, only those many number of electrons will pass. So this nichrome alloy does not show any significant change in its resistivity. Okay. Next we have some metals like semiconductors. Resistivity of semiconductors decreases on increasing temperature. So this we'll study in detail in semiconductors chapters. What happens here is on heating, when we start to heat, what happens? All the electrons, or there are formation of thermal ions. Okay, so if somebody in any is semiconductor started in any of the schools, guys? Is semiconductor started in any of the schools? Yes, no. Hope. Yeah, it might have started, but I guess it should have started. Okay. So what happens in semiconductors? What happens? So when we heat, so if I have a semiconductor, say I have valence band and conduction band. So the valence band has many number of electrons. In semiconductors, the valence band has high concentration of electrons. Okay. So what happens on heating? On heating, so these electrons gain enough energy, enough excitation energy. Okay. So on heating, these electrons at the valence band get enough excitation energy to overcome this energy band or confident energy gap. So they get enough energy to overcome this energy gap. So what happens when I heat it? On heating, these electrons gain more energy and more number of electrons cross this energy gap to reach the conduction band. That way, the conductivity increases. Okay, the conductivity increases in case of semiconductors. On heating, conductivity increases. Okay, this is why the semiconductors does not obey Ohm's law, and on heating there is more conduction of electrons. So the semiconductors does not show any change. Okay, shows that the resistivity decreases. So since conductivity increases, the resistivity obviously decreases. Okay, hope this is understood, guys. So for now, remember only this. So there is some small energy gap between valence band and conduction band. So this small energy gap, there are n number of free electrons inside this valence band. When I supply some heat, so I'll show heat here. So when I heat it, so what happens? These electrons gain enough energy to overcome. So these electrons cross this energy gap, and yes. So I'm talking about intrinsic, okay, intrinsic semiconductors only, pure semiconductors. This is only for pure semiconductors, not for doping. Okay, Bhagat? So on doping, conductivity increases. So we'll come to doping in semiconductors chapter. Okay, we don't want to discuss that here. We'll discuss that in detail in semiconductors chapter only. It will be done by this one only. So what happens on the free electrons on heating? They gain enough energy and they jump to the conduction band. So conductivity increases, resistivity decreases for semiconductors. So semiconductors does not show any significant, does not obey Ohm's law. Okay, shows significant change because the conductivity increases on heating. Okay, cool. So next we have question, guys. Please try to solve this question. The resistance of a platinum wire. So we had missed these three questions. Please check this out. The resistance of a platinum wire okay. The resistance of a platinum wire of platinum resistance thermometer at ice point is 5 meter. Sorry, 5 ohms. So what is given to us? The resistance at 0 degree Celsius is 5 ohms. Okay, so this is nothing but my resistance at 0 degree Celsius. The standard reference temperature. At reference temperature T is equal to 0 degree Celsius, resistance is 5 ohms. At T is equals to some 100 degree Celsius, when the thermometer is inserted into a hot bath. So what is a hot bath? Hot bath is that where we keep boiling water. Okay, so when we have a water tub, so if we take a beaker and keep water, and if we heat this beaker to up to 100 degrees Celsius, when water starts to boil, this is my hot bath. Okay, this is my hot bath. Please remember, this is my hot bath. So these hot bath is maintained at 100 degrees Celsius. So when the temperature was kept at here, my T is 100 degrees Celsius. Okay, capital T. So here T is 0 degrees Celsius and here T is 100 degrees Celsius. The resistance of the platinum wire varies as the resistance of the platinum wire is 5.2 ohms. So at 100 degrees Celsius, it's 5.5 ohm. When the temperature is inserted in the when the thermometer is inserted in a hot bath, the resistance of platinum wire. So when I introduce a thermometer, so the resistance will be 5.2 ohms. So at 100 degrees Celsius, my guys, please remember this. At 0 degrees Celsius, my temperature, my resistance of platinum wire is 5 ohm. At 100 degrees Celsius, my resistance of the platinum wire is 5.5 ohm. At temperature, at a given temperature, when my thermometer was introduced into that hot bath, what happens? Some of the temperature was absorbed by the thermometer. So remaining temperature, my platinum wire shows 5.2 ohms of resistance. Now you have to find the temperature of that hot bath. How to do that? So using RT is equals to R naught into 1 plus alpha T1 minus T2. First, let me calculate what is my alpha. Okay. So we'll calculate our alpha. So I know that RT is for first case where I had the steam point. In first case where I had the steam point, I'll use that to find alpha. To find alpha, so R100 minus R naught into 1 plus alpha into 100 minus 0. Okay, so my final temperature at steam point was 100. Initial temperature was 0 degrees Celsius. So what was the change in resistance, guys? What was the change in resistance? How much was the change in resistance? Is it fine? Guys, are you here? Hope everyone is listening to me. How much was the change in resistance from 0 degrees Celsius to 100 degrees Celsius? No. See, again, I'm going to explain the question. I think some of you got confused. So I have water, okay? So I have water at 0 degrees Celsius. Now I dipped a platinum wire. So I dipped a platinum wire. So this platinum wire, then I try to conduct this platinum wire. This platinum wire had a resistance of R is equal to 5 ohm at 0 degrees Celsius. Now I started to boil this. Okay, I started to boil this. When it started to boil at 100 degrees Celsius, the same platinum wire, okay, had a resistance of 5.5 ohms at 100 degrees Celsius. Okay, R100 at 100 degrees Celsius, it had a resistance of 5.5 ohms. Now what happens at some random temperature RT? So now I have the same setup. So I introduced a thermometer here. Okay, I introduced a thermometer. So I check the temperature. I check the temperature. So now the temperature is not 100 degrees Celsius. It's somewhere between close to 100 degrees Celsius, but less than 100 degrees Celsius. Okay. At this time, at some given temperature, the temperature I don't know the temperature is not mentioned here. Okay. So now the resistance is 5.2 ohms. Now, what is the value of this temperature? What is this temperature? They are asking, what is this temperature? That's the question. Okay, I hope everyone have got the question clearly. So the change in resistance from 0 degree to 100 degrees Celsius, 0.5 ohms. Okay. R100 minus R0 is 0.5 ohms. Hope everyone have got this, guys. Yes. Now, what I need to calculate? I need to calculate the temperature T at 5.2 ohm. What will be its temperature? So at 0 degrees Celsius, it has 5 ohms. At 100 degrees Celsius, it has 5.5 ohms. At 0.2, sorry, at 0.2 change in resistance. Say when the resistance was 5.2 ohm, what was its temperature? So one of is 40 degrees Celsius. Others, you can also try. Okay, first try to calculate your alpha. My alpha value will be R100 minus R0 by 100 R0. So you will equate that to alpha. Then we know that R is equals to R0 into 1 plus alpha delta T. So the change in temperature is T minus 0. So from here, we get RT minus R0 by T R0. So this is the temperature which we have to find. This is the temperature we have to find. Okay. Similarly, we calculated we took the reference as 0 degrees Celsius only, and we had to check the temperature for which the resistance varied to 5.2 ohm. Okay. Now, what happens? So we know that since both are equating to alpha, we can equate these two equations, equation 1 and 2. So please try to equate this and find the answer, guys. Please take 30 seconds of time, okay, 1 minute of time, and try to find out the answer. I want everyone to participate and answer this. Please answer, guys. Come on, guys, come on, try to answer. R100 minus R0 by 100 R0 is equal to R minus R0 by T R0, right? So substitute the values. What is my R100? What is my R100? 100 ohms. R100 ohms is 5.5 ohms minus 5 by 100 into R0 is 5. So 5.5 minus 5 by 100 into 5 equals to 5.2 minus 5 by T into 5. So I had to find the temperature. Please try to simplify this, guys. What is the answer? I'm waiting. Zoom people also could try. Okay. Zoom people, please try to answer, guys. Come on. Okay, Ramakrishna Reddy and Bhargav had given the answer. Cool. Super. Ramakrishna Reddy and Bhargav. Yeah. So yes, guys. So they had given the correct answer. The answer is 40 degrees Celsius. So what happens? 5 minus 5 by 5.5 minus 5 gives 0.5 by 100 into 5. That is 0.5 by 500 is equals to 5.2 by 5. So on equating, trying to equate this, so you'll get T is equals to, or 5T equals to, yes, 5T equals to 5.5 by 100 into divided by 0.2, right? Hope this is right. I mean, we'll get 500 by 0.5 equal minus, let me solve that way. So 0.5 by 500 is equals to 0.2 by 5t. So we had to calculate check for 5t. So I'll get 5t is equals to 0.2 by 0.5 into 500. So I hope everyone tried to solve this. So you'll get T is equals to 40 degrees Celsius. Just try to solve that and you will get T is equals to 40 degrees Celsius. Okay. Next question, guys. So a copper coil has a resistance of 20 degrees Celsius. Sorry, 20 ohms at 0 degrees Celsius. I have a copper coil as a resistance RT is equals to, sorry, R0 is equals to 20 ohms at 0 degrees Celsius, and RT is equals to 26.4 ohms at 80 degrees Celsius. Find out the temperature quotient. What is alpha? Guys, come on, try to answer, please. Yes, come on guys, please try to answer. Shailaja, that's still in degree Celsius, so we keep it in degree Celsius. Okay. I hope everyone is trying this question. So we have more. Yeah, we have more to solve, guys. Come on, big, 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 big. Hope everyone in YouTube is also trying to solve. So we had, okay, what is the formula we use? RT is equals to R naught into 1 plus alpha delta T. So what is my delta T, guys? What is my delta T? So my final temperature is 80. Final temperature minus initial temperature. So 80 minus 0, that is 80 degrees Celsius only. Okay. So yes, since my temperature is 80 degrees Celsius, what will be my RT? So 26.4 is equals to 20 into 1 plus alpha 80, 80 alpha. Okay. So if you try to solve this, what will be your answer? Okay, someone answered in Zoom and it's correct. Guys, others, please try to answer. Someone answered in Zoom and that's correct, guys. Others, please try to answer. Yes, exactly, Madhavi. Madhavi, correct. Madhavi, correct. So yeah, so it's 26.4 by 20 is equals to 1 plus 80 alpha. So if we try to solve this, 26 divided 26.4 divided by 20 is 1.32. We get somewhere around 1.32 minus 1 is equals to 80 alpha. So from here, 0.32 is equals to 80 alpha. So alpha is equals to 80. 0.32 is 80 alpha is equals to 0.32. So alpha is equals to 0.32 by 80. Okay. So we know that 4 is a 4, 4 8 so 8 4s are 32, right? So if we try to equate this, alpha is equals to 320 into 10 power minus 3 divided by 80. So we can try to simplify this. So we'll get alpha is equals to 4 into 10 power minus 3. Okay, so this is the answer. The answer is option A. Okay, option A is the right answer. Yes. So next question we have last one question. So it's a similar question, guys. Instead of RT, they had given you a temperature. Instead of asking you to find the final temperature, they have given you to had given you the temperature itself. Please try to find out, guys, here. So what is given? My R naught is 5 ohms. My R 100. So at 0 degrees Celsius, my resistance is 5 ohm for the same platinum resistance thermometer. So the resistance of platinum wire at 0 degrees Celsius is 5 ohm. The resistance of the same platinum wire at 100 degrees Celsius is 5.23. This case is this question is different. So when the thermometer now, if the same wire is inserted in a temperature of 345.65 degrees Celsius, what will be its resistance? Guys, please try to solve this. So the temperature is now given as 345.65 degrees Celsius. So what will be its resistance now? So again, we are going to use this RT is equals to R naught into 1 plus alpha delta T. So the final temperature minus initial temperature. So the final temperature is, say here again, we have to find the value of alpha first. Okay, we have to find the value of alpha first. So we use R100 is equals to R naught into 1 plus alpha 100 minus 0 degrees. So we'll use this 0 degree Celsius and 100 degree Celsius values to find alpha. So similarly, for this temperature 345.65 degrees Celsius, we'll try to find the value of RT. Then we know that RT is equals to R naught into 1 plus alpha T. On substituting this, so we know the value of alpha equates to this R100 minus R naught by 100 into R naught. So since both of these equations equal to alpha, we try to equate these equations to find the value of my RT. Guys, from here, please try to find the RT. Please substitute all the values and try to find the value of RT. Come on, guys. Yes. I'm waiting for one reply from any one of the students. Like any one of you could reply. Okay, so let's try to substitute. Okay, so we on substituting we get 5.23 minus 5 by 100 into 5 is equals to RT minus 5 by 5.65 into 5. So you will get 5.23. Okay, we'll try to solve here. So you get 0.23 divided by 500 is equals to RT minus 5 by P45 into P45.5 0.65 into 5, that is 1728.25. So on trying to simplify this, you get RT minus 5 equals to 178.25 into 0.23. So that is 397.5. 397.5 divided by 500 RT minus 5. Yeah, somewhere approximately that. 5.795 approximately. Exactly, Ramakrishna Reddy. Cool. So Ramakrishna Reddy had given this answer. Yes, guys, you could try to answer this. So 500 into RT minus 500.5. So divided, I will directly take this divided by 500. So you get RT minus 5 is equals to 0.794. On simplifying, you get RT is 5.794 ohms. Okay, so this is your value for RT. Okay, cool guys. So this was much of it for Ohm's law and temperature dependence of resistance. In today's class, we were supposed to start with the energy, power, and combination of cells and resistances. So let's check that. Okay. Yes. Guys, please let me know if my screen is visible to you all. Guys, let me know, please. Please let me know if my screen is visible to you all. Power, resistance, and cell. No. Power, resistance, and cell. This screen should be visible to all. Yes. Okay, visible to me. Thank you. Thank you, guys. Again. So in today's class, we'll be discussing about the power, resistance, and cell. So what do you mean by power, guys? Electrical power. So how much do you know about electrical power? So we'll be talking about electrical power here. Okay, electrical power, the resistance, electrical resistance, and how a cell works. So we'll just give a brief introduction on cells. So let's begin our class like this. So the learning objectives. So we'll be learning about electrical energy and power. So series combination of resistors, parallel combination of resistors, cells with internal resistance. Okay. So first let's start with electrical energy and power. So what is voltage? What do you mean by voltage? So so by now you might have learned these technical terms, the potential difference, current, Yes, the potential difference current. Yeah, you might have learned this. This you also know as voltage. And this you know the current or the conventional current, right? So we know this voltage, conventional current or current, and potential difference by now. Yes. So we'll be in today's class. We'll be discussing about what is power. So how does this exist? So for that we'll consider. Let us consider a conductor of length L. That A and B be the points, two edges of the conductor. So one end is A, the other end is B. Now when I connect this conductor with the potential, say if I connect a potential difference, or if I connect this conductor, so let me connect a battery to this. So if I connect this conductor with a battery with potential difference V, then at point A, I'll be having a potential VA. At point B, I'll be having a potential VB, and my current flows from point A to B or from VA to VB, right? Guys, I hope everyone knows this. So when I connect yeah, when I connect a potential difference or when I connect a cell to this conductor, what happens? There is a current flowing through this conductor. So here, if we observe the potential at point A or potential at point A, that is VA, is greater than that of VB. So potential at A is more than potential at B. Okay. Now we know that the net potential applied across this conductor is the change in potential difference itself. What is the potential difference? So potential difference is it's nothing but potential difference is nothing but the potential higher potential minus minus lower potential. So it's a difference, right? So it's a difference between higher potential and lower potential. So if we take, I know my higher potential is VA and lower potential is VB. If I take its potential difference, I'll get the net potential applied, the potential difference of the battery, right? So now here I will get my voltage. So V is equals to VA minus VB. Now this change in potential or potential difference is always greater than zero. Now how to calculate this? How to calculate this? We know that the current flowing through a conductor is nothing but the positive charges flow. Right? We had studied this. The flow of positive charges is called as the conventional current. And if I say delta Q amount of charges flow at this, so delta Q amount of positive charges flow in the for the given delta T amount of time. So we know that I is equals to Q upon T, or I is delta Q upon delta T, change in amount of charge for change in time, right? Remember guys, we studied this current as the change in amount of charge for change in amount of time. So on rearranging this, we get delta Q is equals to I delta T. Now, yes, the energy associated at point A. So there is some limit. So since we have represented the potential difference by V, I have removed the battery. So that helps me solve this. So what happens? So the energy associated at point A is given by 2 times of VA. Is this correct, guys? So is my energy? Hope most of you might be having this confusion. So there exists an energy. Now the change in energy associated is given by change in potential energy. So the change in energy, there exists a higher energy at VA, there exists a lower energy at VB. Now there is change in energy, and because of the change in the current is flowing, the charges are flowing. So how much is this change in energy? So there exists a change in potential energy, that is nothing but final potential energy minus initial potential energy. Now what is that potential energy? So how did we arrive at this equation? So we know that. So guys, please let me know what is my energy stored? Energy, or what is the force on the conductor? So force on a charge. Say if I apply a potential difference, there exists an electric field, right? Right. There might be bit confusion, sir. How did we get Q into VA? For that, let me give a brief description. So when we apply a potential, what happens? There exists an electric field. Correct? Huh? Yes, guys. If you don't reply, how can I continue? Please give some reply, formal or informal somewhere. Okay, thumbs up. Yes, no, something like that. Yes, yeah. So yeah, there is some sort of charges Q. So we know that what is the force acting on these charges? So what is the force acting on these charges? Exactly, Balaam. Super. So it's nothing but Q into E, right? So here, since I have all charges are positive and I have given the magnitude of net charge as capital Q, I'll take this also capital Q. So my F is equals to Q times of E. Now, what is the length of this conductor? So we know that the work done. So whenever I have energy, the energy is nothing but my work done. Or the energy is nothing but my work done, right? So what is my work done, guys? In terms, again, my work done can be written as force into the displacement. Here the displacement is nothing but equivalent to that of the length of the wire or length of this conductor. Correct? Now, the force or the displacement is nothing but the length of this conductor. My charge is even a single charge is having a displacement of total length of this conductor, that is length L. So if I have a charge plus Q here, this charge will move all the way from this end A to this end B. So it's completing the total length or total displacement of L, right? So I can write my displacement as L. So again, guys, so we know that E dot L. What is E dot L or E dot D? Yes. What is my E dot D? Exactly, Madhavi. I'm coming to that equation. What is my E dot D or E dot L? This is nothing but my B. From here, I can write, yes, F, Q into E. I know F is equals to Q to E. So I know the work done or energy stored is F into L. So I can replace this as Q into E dot L. So on rewriting this, I can write this as E dot L as B. So I'll get work done or energy. So my energy is nothing but Q into V. Hope everyone have got this. How we got Q into V as energy. If somebody had any doubts how we got Q into V as energy, this was the explanation. So the change in potential energy, since we told that my point A has higher potential and point B has lower potential, the change in potential energy or change in energy is given by final energy minus initial energy, right? So which is my final energy? My final energy is B and initial energy was A. So the change in energy, delta V, the change in potential. So we know that Q energy is nothing but Q into V, energy is QV. So the change in energy is nothing but Q into delta V or delta Q times of delta V. So my change in potential energy is delta Q times of delta V. So what is my delta V? What is my delta V? Delta V is nothing but final potential minus initial potential. That is VB minus VA. This is final and this is initial always. So we take delta as change in final minus initial. So on rewriting this, we get the change in potential energy is delta Q times of VB minus VA. That is, yes, what is since VB is having lower potential than VA, it will be always negative. Now we can write this as, yes, we know that delta Q is I into delta T. We can write this as minus I times of V times of delta T. So this is always less than 0. Or we can say the change in potential energy, or sorry, we know that the change in energy, the change in kinetic energy, okay, the change in kinetic energy K is nothing but the amount of work done for moving charges. Okay. In previous case, in our electrostatic chapter, we had the stationary charges where we got that the change in potential energy, the change in potential energy was equals to work done. But here, since my charges were moving, the charges are moving in both the directions. So positive charges moves from left to right, So the change in kinetic energy of these charges is nothing but the work done. So this is given as the change in kinetic energy delta K is equals to minus of delta U potential energy. So guys, if you want to, okay, this can be related as a waterfall. Okay, say if I have some waterfall, so if I have some dam here, and there is lots of amount of water here. Okay, so what happens? My water will be having high potential energy or kinetic energy. This can be analyzed equivalent to that of a water in a dam. Okay, so if I have a dam, in a dam there is lot of water. There is lots of water, and this water has higher potential energy. Right? It has high potential energy. When I open the gates, what happens? The water starts to flow, and all the potential energy is converted to kinetic energy. Right? Yes. So that way, the same way, when my charges were stored inside the battery, when my charges were stored inside the battery, it had higher potential energy. When I allow them to flow, they gain the same amount of kinetic energy. So these both have the same amount of work done, right? These both, the total potential energy and total kinetic energy in a system is always conserved. Hope this is understood by all. Yes? Cool, guys. Okay, thanks for response. Yeah. That way, the change in potential energy, or sorry, the change in kinetic energy is nothing but a change in potential energy. It's always minus of potential energy. We also studied in our previous chapter. In electrostatics also, we consider the change in the external work done is nothing but the change in negative of minus of change in potential energy. So that's the same thing which we are going to see here also. If charges move without collision to the conductor, then the change in kinetic energy is nothing but minus of change in potential energy, negative of change in potential energy. Okay, so that is the kinetic energy. So therefore, the change in kinetic energy is given by I into delta T times of V. So what am I trying to express here, guys? What am I trying to say here? We are going to derive this expression for power, okay? So we know that the change in power or work done by time taken. So what am I coming to here is, so I know that the change in kinetic energy is nothing but, the change in kinetic energy delta KE is nothing but the current flowing through the conductor into voltage, potential difference applied, times the time, the change in time. Now, if I take this delta T in the denominator of left hand side, what happens? I'll get the change in kinetic energy upon changing time, that is equals to I into V. Now, this change in kinetic energy again. I know it as what? I know this change in kinetic energy as what? The work done. So the change in work done, or sorry, the work done by time taken is equals to I into V. Now, what is this work done? What is work done by time taken? In physics 11th standard we had studied. So we are correlating all the things, guys. So yes, this is nothing but, yeah, the power, the electrical power. Then if we try to write the expression, we can write the expression for power as P is equals to V into I. Okay, so this is the relation which shows the potential and the current flow has some power. The power of electrons, or the power stored in that battery when the current flows through the conductor. This power is given by P is equals to V into I. Okay, cool, guys. So this was the only thing which we were trying to say. So from here you have to remember only this power is equals to the power, electrical power stored inside a conductor is given by V into I. That's the thing. Okay, that's what we are going to derive or discuss. So what we discussed, so initially we consider the conductor of some length L. So the left part had a higher potential. So when I connected this to a battery, so the positive end of the battery had higher potential and negative end of the battery had lower potential, V and VB. So yes. So VA was greater than VB. So V is equal to VA minus VB was taken. Then from here we check that the energy stored inside the conductor or inside the battery was given by U is equal to Q into V. From the initial expression I is equal to Q by T, delta Q by delta T, we got this, the total charge is delta Q is equal to into delta V. Then when I connect this power or when I connect this potential, a potential difference, there is flow of charges and there is change in energy at the two ends of the conductor. That change in energy is given by change in potential energy, that is final potential energy minus initial potential energy. So whatever the potential energy stored inside the battery is discharged inside in the conductor. So whatever the potential energy stored in the battery is discharged in the conductor as kinetic energy. So these charges which were stored inside the battery as stationary charges had potential energy. When they are connected to the conductor, they start to move due to the potential difference. So this change in potential difference or this change in potential difference is equivalent to the kinetic energy possessed by these charges. So the change in potential energy or the change in kinetic energy is given by negative of potential energy. So this change in kinetic energy was also the amount of work done by the battery to move these charges. So that change in kinetic energy on equating we get. So the change in kinetic energy is negative of potential energy. So on substituting these values, the kinetic energy is negative of negative I into V delta T was given. From here, negative negative cancels. So the changing kinetic energy is nothing but the changing kinetic energy is given by I into V into delta T. So this is always greater than zero for a positive power. So on rearranging the terms, we get that the change in kinetic energy upon time taken is nothing but the power stored in the battery or the power in any electric circuit is given by P is equals to V to I. So this is the expression. So but the charges collide with ions and atoms during transit. So power is nothing but delta W by delta T. So we got that P is equals to V into I is an expression. From Ohm's law, we know that again guys from Ohm's law, we know that V is equals to IR and I is equals to V by R. So on substituting, so we know that P is equals to V into I. Putting this equation 1 in this equation E, putting equation 1 in equation we get P is equals to I square times of R. So this is one expression. Again, putting equation 2 in equation E, we get P is equals to V square by R. So these two are the other two variants of the same expression. Okay, so we know the basic expression for power. Power in an electrical circuit is given by P is equals to V into I. Okay, now this two can again be altered as P is equals to I square R, and this is the same as V square by R. Okay, this is called as the electrical power base. I hope all of you have understood electrical power how we got. So from here, please take only the three formulas: P is equals to V to I, P is equals to I square R, and P is equals to V square by R. Okay. Yes. Next, so in a conductor, so what is happening to this power? So what is happening to this power in a conductor? So this power, so whenever there are free electrons or whenever there are these charges flowing inside the conductor, we said they collide, right? So they collide and they the power, more amount of power is required to make them push or make them flow. So this power is dropped or there is some power loss inside a conductor whenever there is the flow of current. So this power loss in a conductor is wasted as heat. Okay, the power inside the conductor is lost as heat, and it lost as heat inside the resistance of the conductor. Because of the resistance, so there were some collisions between the charges when they are flowing, right? So these collisions is nothing but the resistance of the conductor, and this resistance causes power loss. It doesn't allow the flow of conduct current. So this resistance is the reason for power loss. This power loss is in the form of heat. So whenever there is more collisions between the electrons and the atoms, what happens? That energy is lost as heat inside the conductor. Okay, please remember that. So whenever they ask you to find the heat loss or heat in the conductor, They're just asking you to find the power. Okay, guys, please remember this. This is very, very important. Whenever they are asking you to find the heat loss in the conductor, they are just asking you to find the power lost. So which formula we are going to use in that case? We are going to use any of these three formulas. P is equals to vi, p is equals to I square r, or p is equals to v square by r. Any of these to calculate the heat lost in a conductor, also the same power. So heat loss is nothing but the power loss in a conductor. I hope that is understood again. Please give a confirmation. Yes. Yes, thank you. So from power station, yeah. So we get power in our power station. What happens? So we have the generators in the power station. They generate power and they supply through the They step up power through transmission lines. I mean through a transformer, then through transmission lines. The transmission lines again step down the power at the transformer. Again they get power, supply the power to our homes. So this power is given by P is equals to I into V. So the connecting wires from the power station to the device has a finite resistance RC. So the power wasted in the connecting wires is given by PC is equals to I square RC. Okay. So it's the general relation between power, or in on trying to substitute the other form of Ohm's law, that is I is equals to V by R. I is equals to V by R. You would get the same expression. So this is nothing but PC is inversely proportional to voltage square. Okay, so more my voltage, less the power loss. So most of you might be studying this. So we know that from Ohm's law we get P is equals to VI. We had two expressions from here again. So P is equals to V square V by R, V square by R, or P is equals to I square R. Okay, so what causes me to more power loss? Is it the current or is it the voltage? So you might have learned in your AC chapter, in your alternating currents chapter, why do we always step up the voltage or step down the voltage only? Why not we do the same with current? So this is the reason, guys. So my power lost inside the conductors is given by is inversely proportional to voltage. Okay, it's inversely proportional to voltage square. The power lost inside a conductor is inversely proportional to voltage square. If I increase, if I step up my voltage, if I increase the voltage, say my generation level is somewhere around 415 volts. I step up my voltage up to 33,000 volts, okay, or 11,000 volts. So if the generation is somewhere around 1 kV, okay, let me take 1000 volts. I'll step up to 11,000 volts, then transmit. Again, when I'm taking, I'll take 11,000 volts and step down to 1000 volts. Actually, 1100 volts should be 1.1 kV. Then again, it's further step down to 230 volts and supply to your home. Okay. So here in your poles you have a separate transformer which will again reduce this 1000 volts to 230 volts. For industries it will step down to 450 volts. So this we will study in detail again in our AC chapter. Okay. So don't worry much. So next we'll have combination of resistors. So there are series and parallel combinations. So in our previous chapter of capacitor, we learned about the series and parallel combination of capacitors. Similarly, in today's class we'll be learning about series combination of capacitors. So let us consider two resistors. Sorry, we'll be studying about series combination of resistors. Okay, not capacitors. We'll be studying about resistors. So we have two resistors. So the two resistors are said to be in series even only if their endpoints. Say if I have two ends R1, say if I consider a resistor, in previous class we studied about resistor, right? The circuit symbol of resistor is given by this. So guys, a resistor is shown by this symbol, okay? So it's the straight line with some corrugated lines. So we call this as corrugated lines. Okay, straight line with corrugated lines is the circuit symbol of resistor. Please remember this. So if we have two resistors, if we consider two resistors, and if we connect one end of the resistor with other end, So if I want to name them A and B again, if I connect the B end of one resistor with A end of other resistor, this combination is called as series combination. Okay. Yep. So if I have two resistors connected in series, the current flowing through the resistors will remain same, but the voltage across the resistors will be different. Please remember this. Again, we had discussed this in the capacitors as the charges flowing through the capacitors was same, but the voltage drop was different. Okay. Similarly, when we connect two resistors in series, the resistance have the same amount of current flowing through them, but different potential across them. Then the potential across them, if the total potential applied is V, then the change in potential. So the total potential is given by this expression V is equal to V1 plus V2. So we know V1 from Ohm's law, we know that V is equal to I into R. From there, we can calculate V1 as V1 is equal to I times of R1, V2 as I times of R2. So V will be equal to I R1 plus I R2. So that is I into R1 plus R2. So the R equivalent will be equal to nothing but V by I, that is R1 plus R2. So therefore, if we have any number of resistors connected in series, so if we have, say, if we have one more resistors connected in series with R1, R2, R3, then we get R equivalent is equals to R1 plus R2 plus R3. Say, likewise, yeah, if we have n number of resistors connected in series, then the equivalent resistance will be summation of all the resistors connected in series. Okay, this is the series combination of resistors. Guys, got this? So I hope you all know this, right? So R equivalent, the equivalent resistance of resistors connected in series is equals to the sum of all individual resistors. Okay, the equivalent resistance is the sum of all individual resistance connected in series combination. Okay, say if R1 equals to R2 equals to if all these resistors, say if R1 equals to R2 equals to R3 equals to etc. all are equals to Rn equals to R. If all these resistors are equal to R, then what is my R equivalent? What is my R equivalent? It's nothing but R equivalent is equals to n times of R. Okay. So R equivalent is again summation of R. So that is n times of R. Or this is I times of R. Okay. We can write the same thing as this. Okay. So this is my series combination of resistors. Similarly, if I consider, okay, let us solve a problem regarding this. Say there are three resistors, 2 ohm, 4 ohm, 6 ohm are connected in series. Find the equivalent resistance. What's the equivalent resistance? Yes, reply fast. 2 ohm resistors, 4 ohm resistor, and 6 ohm resistors connected in series. What is their respective resistance? Are equivalent. 2 ohm, 4 ohm, 6 ohm. 2 ohm, 4 ohm, 6 ohms. So 6 plus 4, 10, 10 plus 2, 12. Yes, exactly. So R equivalent is 12 ohms. Okay. R equivalent is 12 ohms. Cool. Super guys. Awesome. Next. So we have parallel combination of resistors. Say if two or more resistors are said to be parallel, if one end of all the resistors, if both the ends of all the resistors are connected or joined together in similar ends. Say if I have end A of resistor R1 and end B of resistor R2. Say if I have end A of resistor R1 connected to end A of R2, similarly end B of R1 resistor is connected to end B of R2, then these two combination of resistors, then we can say these two resistors are connected in parallel. So the effective resistance, then now the current flowing through this resistors, okay, the current flowing through this resistors varies, but the voltage remains the same. Okay, the voltage drop across these resistors remains the same, but the current flowing through these resistors varies. Now applying Ohm's law, we know that V is equals to I into R1 and V is equals to I2 into R2. Since there are two different currents flowing through here, the current is given as the total current going through this parallel combination is given by I is equals to I1 plus I2, that is V by R1 from Ohm's law. I is equals to V by R, right? From here we get I1 is equals to V by R1 plus I2 is equals to V by R2. On simplifying, we get V, or yeah, I is equals to V by R. Then V by R is equals to V into 1 by R1 plus 1 by R2. So from here we get the R equivalent. So I is equals to V by R equivalent. So that is given by R equivalent is 1 by R equivalent is equals to 1 by R1. Right, sorry for this. So 1 by R equivalent is equals to 1 by R1 plus 1 by R2. This is the effective resistance. So guys, if you want to simplify for this, what will be my R equivalent? In this case, if we want to simplify for this, what will be my R equivalent? So it will be R1 plus R2 by R1 R2. Is that R1 R2 by R? Okay. R1 R2 by R1 plus R2. R1 R2 divided by R1 plus R2. This is my R equivalent for this. Say, yeah, again, if I have third resistors connected in parallel, then the current flowing through the net current, the total current flowing through this combination would be I1 plus I2 plus I3, I is equals to I1 plus I2 plus I3. From here, V is equals to I3 into I3 into R3. So the net current I is from Ohm's law, we know that I is equals to V by R. So we will be using the same expression. I is equals to V by R1 plus V by R2 plus V by R3. That is V into 1 by R1 plus R2 plus R3. So that is for resistors, n number of resistors connected in parallel, we get 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus 1 by R3 plus etc. plus 1 by R. So this is the combination of resistance in parallel. Okay. So let's try a problem for this. Guys, please try to find the equivalent resistance of this combination. Okay. So find the current I in the circuit as shown in the figure first. So to solve this, first let me know what is my R equivalent. What is the R equivalent? Yes, guys, come on, please try to solve this. Find the R equivalent here. So have three resistors, each 30 ohms connected in a triangular fashion, and say two ends of the triangle is connected to a 2 volts battery. Now, what is my R equivalent in this case? Then find the total current in this combination. Yes, it's cool. Super Krishmurti. Others, please try to answer this. So, guys, is there any series combination here? Is there any series combination here? Yes, there is a series combination. That is 30 plus 30. So, if you try to start simplifying, so the 30 plus 30 will become 60 ohms, right? So, there are two resistors connected in series. That is 30 plus 30, that is 60 ohms. Now, on simplifying, we get, yeah, 30 ohms parallel with 60 ohms. Another yes, there is a series combination. Please check that. Yeah. So 30 plus 30, that is 60 ohms. So for series and parallel, we have 60 ohm parallel with 30 ohms. So 1 by 30 plus 1 by 60, that is 1 by 20. So you get R equivalent is 20 ohms. Okay. So R equivalent is 20 ohms. Since my R equivalent is 20 ohms, so I got R equivalent, its value is 20 ohms. And I have connected a battery of 3 is equals to 2 volts. What is my current I? I is equals to V by R. Right. So on simplifying, we get 2 by 20, that is 1 by 10 amperes. Okay, so the current value is 0.1 amperes. Correct question will be Rakesh. ಏನು ಮಾಡೋದು ಗೊತ್ತಾಗ್ತಿಲ್ಲ ನನಗೆ. Please note, please check that do the research and introduction, Rakesh. Okay. So next question. Let us come to this question. Okay, compute the equivalent resistance of this network shown in the figure. Guys, find and also find the current from the battery. So have 6 ohm in parallel with 3 ohm and series with 4 ohm. So guys, how you should be on looking at the circuit only, you should calculate all the resistance values in your mind. Okay, super Shailaja, awesome. Shailaja, is that answer for this question also the same? So 6 3 by 6 plus 9, 18 by 9, 2 2 4 6. Okay, okay. So the current answer, guys, please give me the answer. What's the current flowing through this? See, no need to. Observe this circuit. How is it? So 6 parallel 3. So we know that. Yes, exactly correct. Krishna, the correct answer. Namakrishna, the correct answer. Madhav, the correct answer. Prakash, check your answer. Prakash Goda, check your answer. Adarsh, correct answer. Lakshmi, the correct answer. Others, Zoom people, please try to answer, guys. Others, say 6 and 3 is in parallel combination. So how to solve this? You know that R parallel. So 6 into 3 by 6 plus 3. So guys, please apply this. 6 into 3 by 6 plus 3. That is 18 by 9. 2 ohms. Right. So in series with 4 ohm. So 2 plus 4 is 6. 6 ohm. Now the total resistance, so the total voltage applied is 80 volts and 6 ohms. So I is equal to V by R, that is 18 by 6, that is 3 amperes. Okay. Prakash Gora, please check that answer. I hope you have got that by now. 3 amperes. 18 by 6 is 3 amperes. 18 by 6 is 3, so the total current is 3 amperes. Okay. So next, guys. So what we have in day-to-day cell, so we have that cell, right? In the previous class, we had checked that cell. So what is a cell, guys? What is a cell? So we'll solve more questions, guys. I'll be giving you more questions to practice, but we have to complete the theory part first. So we'll be solving the very huge number of questions on this. Okay, there are plenty of questions. You should practice in such a way that you will be very crystal clear with these topics. ಯಾವ ತರ ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡ್ತೀರಾ ಅಂದ್ರೆ on looking the circuit only you have to identify. On looking at the circuit only, it should be you have to calculate everything in your mind and give the answer. You should not touch your pen and paper. No touching of pen and paper. You should calculate everything in your mind only. Okay. Last topic which we are going to study today is cells and cells with internal resistance. So guys, in our previous class, we know that one of the sources of electrical energy is a cell. Okay, one of the sources for electrical energy is a cell. What is a cell, guys? How is a cell constructed? How do we get a cell? So we'll just give an introduction to this. So we'll be discussing about cell. So I'll just give you a brief introduction about cell, and so next we'll be discussing about combination of cells and resistor. So that's the only part left. What? No, why is this happening? So what is a cell, guys? Cool, Marco, super. So cell head in general head is be as simple as possible. Okay. In meantime, I'll launch you the technique. I mean, teachers and peers for all Zoom audience. Guys, please respond to this. This is very necessary for us. Unfortunately, there are only 4 students now. ಯಾಕೆ ಇಷ್ಟು ಕಡಿಮೆ ಆಯ್ತು ಜನ? I don't know why there are less number of students today. Is it because of your exams? Okay. So there are four students. I want all four students to reply to this so that I can complete this. So I can focus more on study. I mean, completing syllabus, guys. One more. Like okay. Okay, you can close that if you could start. So, what's a battery, guys? So, we will come to this discussion. What's a battery? A battery or a cell? What is it? Cell or a battery? So, cell or a battery is an electrochemical device, right? Electrochemical device. So, what happens in this? So, there will be formation. Say, you might have learned this reactions. I hope most of you might have learned this redox reactions in your previous class. By now, you might have learned this, right? The redox reactions. Yes, reduction and oxidation. Okay, so what happens? Say if I have a metal rod, metal conductor dipped in its salt solution. Metal, say if I have a metal conductor dipped in its salt solution, and this is another metal rod again, another metal rod again dipped in its own salt solution. Say for example, if I have copper here, copper and zinc. Okay, if I have two metals, say if I dip this copper in copper sulfate, Cu2SO4, right? Please correct me. Mhm. So copper in copper sulfate and zinc in zinc sulfate. So if I dip copper in copper sulfate and zinc in zinc sulfate, what happens? And if I connect these two, if I by some means connect these two with a KOH solution, I hope most of you have learned Daniel cell, electric cell, which you guys might have learned in your chemistry class. So we have such arrangement. What happens? There will be some electrical, I mean, chemical changes, chemical reactions happening, and this chemical reactions give rise to an electric current. Give rise to an electric current between these. So one of these electrodes become positively charged, and other of the electrodes become negatively charged. Hold on. Now, yes. So since at point A, say if I consider there was this electrode which became positively charged, exhibiting redox reaction. Yes, cathode and anode. Yeah, exactly, Lakshmi. So one as at A it is positive charge, and yeah, at B it is negatively charged. So my potential at A will be greater than 0, and the potential B will be, yes, again less than or greater than. Potential would be, magnitude of potential would be greater than 0, but its sign is negative. Okay, so the net potential, the potential difference between them, between P and N, is given by P positive. The potential difference is taken as positive potential minus negative potential, right? So that is V positive minus V negative. On equating, we get the potential difference as E is equal to V positive plus V negative. So it's always greater than 0. This is the EMF. This is the EMF. EMF E is the potential difference between the positive and negative electrodes in a circuit. Okay, this is how a battery works. So the potential difference across the battery is given by E is equal to V positive plus V negative. So this is positive potential, the positive rod potential P and negative rod potential N. Its difference is taken as P minus Vn, or V positive plus of V negative, and it's always greater than 0. Okay, when we connect an external circuit to this, so there exists the flow of electrons in the opposite direction. So the flow of electrons is from the negative side to positive side, and the electrolyte, all the electrolytes flow in this direction. The flow of electrons. So since my electrons flow in this direction, all the positive charges inside the battery flow from this side to this side from B to A. So this flow of positive charges constitutes a current. So all the positive charges flow in this direction, and all the negative electrodes or negative ions flow in this direction. So what happens? The Cu plus is the Cu, when it's dipped in its solution, it becomes U plus, and this Zn, when it's dipped in solution, it becomes Zn minus. So they exhibit a positive charge and a negative charge on their electrodes. From here you get the battery. So this you might have learned in your chemistry. Again, then we come to the physics point of view. The potential, the net potential is V plus V minus, that is greater than zero. So the change in potential, yes, this is the discharging current. This is the charging of the battery and discharging of the battery. On discharging of the battery, the change in potential is given by V plus V minus the summation, the total net potential or net EMF of the battery E minus the current times of the resistance. Here, since the electrodes, copper and zinc electrodes dipped, may have or will have practical in real life, these will have some small amount of resistance. Since this is also a metal, this is a metal and this is a metal, these two metals have different conductivities, right? These two metals have different conductivities and they also have different resistivities. These resistivities add up to give a small r. This is called as the internal resistance. So there will be something called as internal resistance of the battery. The battery inherently, because of these electrodes present in it, have some internal resistance. Okay, so that is given by the net potential is then given by E minus IR. That R is the internal resistance of the battery. Then when we connect this to an external resistance, there will be some change. So this entire battery setup or this entire cell setup is replaced by two electrodes, two rods, a bigger rod and a bigger line and a smaller line. This is called as a cell, and this equivalent circuit symbol is represented here. So by applying Ohm's law, we get V is equals to IR. So IR is equals to E minus IR, where small r is called as the internal resistance of the battery. Okay, this is much of it. So I is equal to T by R plus R. So we have one small problem. So the problem is a battery of EMF 2 volts with internal resistance 0.1 ohm is connected, is being discharged by a current of 5 amperes. Calculate the potential between the terminals. So we have to apply V is equal to I into R. So that is 5 into 0.1. Since the internal resistance of the battery is 0.1 ohms, we have to connect that. So 5 amperes into 0.1, that is 0.5 volts. Since I have connected a battery of 2 volts, the potential drop across this, the potential drop across this is 0.5 volts. So yes. So the total potential across this, the total potential across this ends. So if I call just A and if I call just B, the total potential across A and B would be 2 volts plus 0.5 volts, that is 0.5 volts. Okay. So guys, this was the small problem. So in the end, we have to say that each and every battery has its own internal resistance. Okay, all the batteries will be having its own internal resistance, which is of negligible value. But sometimes this negligible value is also counted for the calculation of current going through any external device. Okay, this is it. This is much of it. So tomorrow's class will be discussing about Kirchhoff's laws. Okay. In tomorrow's class, we'll be discussing about Kirchhoff's laws and series and parallel combination of these cells also. Okay. Please come prepared and we will disconnect now. Thank you guys. See you again in tomorrow's class. Bye bye. And please note that make more students participate in the class, guys. This strength is very low. Okay. Okay, guys. We are being late to the next class.